Did life ever exist on Mars? And if it did, is it possible that our own story on Earth began there? It is one of the most captivating ideas in science, but the responsible answer today is careful. Mars has not yet shown evidence of past life. What it has shown is something slightly less dramatic, but scientifically just as important. Promising places to look, promising kinds of chemistry, and a much clearer sense of what would count as real evidence if life ever did leave a detectable trace. That distinction matters. In astrobiology, water is not life. Organic molecules are not necessarily biological, and an intriguing signal is not proof. Serious claims need multiple independent lines of evidence that, taken together, make non-biological explanations extremely unlikely. Mars is a perfect example of why that standard exists. The planet we see today is cold, dry, and hostile at the surface. But billions of years ago, the picture appears to have been very different. Orbiters and rovers have revealed branching valleys, lake basins, sediment fans, and signs of ancient flowing water. There were rivers. There were lakes. At some times, there may even have been larger standing bodies of water, perhaps in northern basins that looked something like an ocean, though that part remains uncertain. The most persuasive geological clues are not just isolated channels, but whole drainage patterns. From orbit, scientists can see valley networks that branch in ways more consistent with sustained surface runoff than with a single catastrophic flood. And where water slows down, it drops sediment. That is why deltas matter so much. They sort, concentrate, and preserve material. On Earth, they can act like environmental archives. On Mars, they may be among the best places to search for ancient biosignatures. This is a big reason why NASA sent Perseverance to Jezero crater. Jezero once held a lake, fed by a river that built a delta into the basin. In a setting like that, sediments could accumulate layer by layer, water could react with rock, and organic compounds, if present, might be trapped and preserved. In other words, Jezero is not just a place where water existed, it is a place where the right kinds of samples might still exist. And habitability is really the key word here. Early Mars may have offered regional, temporary niches where life could in principle have emerged or survived. Water, energy sources, mineral surfaces, chemical gradients, and enough time for chemistry to do something interesting. But that does not mean all of Mars was warm and wet, or that these habitable conditions lasted globally or continuously. That remains uncertain. Even so, some Martian environments look especially attractive from a microbial point of view. Perseverance is studying sedimentary rocks, carbonates, clays, and other deposits formed in watery settings. These materials are valuable because they can preserve environmental context, and because chemically active boundaries within them may once have supported stable redox gradients. Those gradients matter because microbes, if they existed, could potentially have used them as an energy source. That brings us to one of the most discussed recent targets, Cheyava Falls. This sample drew attention because it appears to bring several interesting things together in one place. It comes from a rock formed in an ancient watery environment. It shows organic signals. It includes certain mineral associations, and it contains redox-related patterns that suggest chemically active conditions in the past. Taken together, that makes it a candidate biosignature. The cautious biological reading is tempting. Perhaps microbes once exploited chemical gradients in that environment and left behind traces that connect water, chemistry, and biology. That is a legitimate scientific possibility. But it is only an uncertain possibility. The very same patterns could also be produced without life. Circulating mineral-rich fluids can reshape rocks in complicated ways. Iron minerals can transform through purely geochemical processes. Hydrothermal activity can generate striking textures and chemical contrasts. Organic compounds can form abiotically or be transported in from elsewhere. So Cheyava Falls is interesting precisely because it sits at the boundary between promise and ambiguity. It is a candidate, not a verdict. That ambiguity is not a weakness in the science. It is the science. Mars is full of processes that can imitate what, in another setting, might look suggestive of life. Water can shape rock without biology. Organics can arrive on meteorites, form in water-rock reactions, or emerge through UV-driven chemistry. Salts, oxidation, and hydrothermal systems can create mineral patterns and redox features that seem exciting, but are not biological. On Mars especially, every signal has to survive very tough source criticism. Curiosity, the rover exploring Gale crater, has added another piece to this picture. It detected long-chain organic compounds, an important result because it suggests Mars can preserve relatively fragile organic chemistry better than many researchers once assumed. That raises the value of ancient Martian sediments as chemical archives. But again, the caution matters. Long-chain organics are not proof of life. They can also form through geochemical reactions, through thermal transformation of other materials, or through delivery from space. And whatever survives on Mars today has not been sitting in a protective museum display. It has been exposed, altered, broken down, reworked, and chemically attacked over immense spans of time. Radiation, ultraviolet light, oxidation, and simple decay all complicate the story. In fact, the Martian surface is generally a poor place to preserve delicate biosignatures. If life ever existed there, many traces may have been erased. That is why scientists care so much about protected environments, deeper rocks, buried sediments, salts, clays, carbonates, and the subsurface. These are the places where a signal, if one exists, has the best chance of surviving over billions of years. So what would it take to move from interesting to convincing? Probably not one dramatic image or one molecule. It would take context and convergence. You would want the geology to show a habitable environment. You would want chemistry that fits biological processing. You would want textures, mineralogy, isotopic patterns, or spatial relationships that all point the same way. Most importantly, you would need those clues to survive intense attempts to explain them abiotically. There is a cautionary precedent here. In the 1990s, the Martian meteorite ALH-84001 was presented as possible evidence of fossil life from Mars. It was a huge story. But over time, stronger non-biological explanations proved more persuasive. That episode still shapes the field today. It reminded researchers that extraordinary claims can collapse if the abiotic case remains strong. It also highlights another major issue: contamination. If samples from Mars are ever returned to Earth, credibility will depend on proving that any detected signal is truly Martian and not introduced from Earth, spacecraft hardware, handling, or later laboratory work. That is not a side concern. It is central. And this leads to the second half of the question. If life did exist on Mars, could ours have come from there? Surprisingly, that idea is not science fiction. Rocks really can travel between planets. We know this because pieces of Mars have already arrived on Earth as meteorites. A sufficiently large impact can blast rock off Mars, some of it can survive space transit, and some of it can land here. The more provocative possibility is that life, or at least microbes, might survive the trip if shielded inside rock. Models and experiments suggest that survival through ejection, transit, and atmospheric entry is not impossible. So panspermia between Mars and Earth is a serious possibility and mechanism. What remains unproven is the actual transfer of life. If life on both planets turned out to be related, that would be profound. It could mean biology originated once in our local planetary neighborhood and then spread, either from Mars to Earth or from Earth to Mars. If, on the other hand, life arose independently on both worlds, that would be arguably even more astonishing, because it would suggest that life emerges more readily when conditions allow. Right now, though, we are not there yet. We do not know whether Mars ever hosted life at all. What we do know is narrower, but still remarkable. Ancient Mars was likely much wetter. It had environments that appear habitable, at least regionally and temporarily. Jezero crater is a strong target because it preserves a lake and delta system where sediments, water-rock reactions, and possible organics may have been archived. Cheyava Falls is scientifically compelling because it combines organic signals, mineral associations, and redox patterns in an ancient watery setting. Curiosity's findings show that Mars can preserve complex organics better than many expected. And yet every one of those signals still has plausible abiotic explanations. So the honest conclusion is this: the evidence today supports past habitability and chemically interesting, well-contextualized search targets, not proof of Martian life. If that proof ever comes, it will likely require returned samples, studied on Earth with the cleanest possible methods and the full power of terrestrial laboratories. Mars has not answered the question yet, but it has told us where to keep looking and how high the bar must be when we think we may finally have found something alive in its ancient stones. Subscribe, enable notifications, and suggest the next topic in the comments.